Ever wonder what makes a lemon pucker?
Or gives baking soda its cleaning power.
You're about to find out.
Because today's deep dive is all about acids and bases. And
Oh.
hold on to your hats because we're going way, way beyond your basic kitchen chemistry here.
We're talking university-level inorganic chemistry, folks. But
Oh.
don't worry.
Don't worry.
I've got my trusty expert guide to break it all down in a way that even I can understand.
That's where I come in.
So,
We're tackling a lecture all about Bronsted and Lewis acidity. And trust me, it gets way cooler than it sounds.
because this isn't just some theoretical mumbo-jumbo, right?
Exactly.
We're talking about forces that shape our world.
Yeah?
In some pretty surprising ways.
Take something as simple as how fast metal dissolves in acid.
Okay.
That single reaction has huge GE implications for everything from how quickly a sculptor can etch a masterpiece
Right.
to the durability of materials used in construction.
So no pressure acids.
Right.
But you're kind of responsible for keeping buildings standing and art looking fabulous.
Yeah. But it goes even further than that.
Right.
This lecture mentions something about ecosystems.
Right. Think about the delicate balance of acidity in our oceans.
Okay.
Even a slight shift in pH can disrupt the whole system.
Wow.
We're talking about things like shellfish not being able to form their shells properly,
Oh, wow.
which then disrupts the food chain and could even lead to ecological collapse.
Okay, that's officially way more intense than I thought acids and bases could be.
And we haven't even touched on what's happening inside your own body.
Oh, right.
Acids and bases are essential for processes like digestion.
Oh, right. Like that burning sensation you get after a big spicy meal.
Exactly.
That's partially hydrochloric acid hard at work in your stomach.
Exactly. So, while we might not always think about them, acids and bases are involved in some pretty fundamental processes.
Yeah.
This lecture dives into two main definitions: Bronsted acids and Lewis acids.
Okay.
Let's start with the Bronsted-Lowry definition, shall we?
Lead the way. Okay, so imagine a game of hot potato, but instead of a potato, we're tossing around a proton.
Okay.
Now, a proton is just a positively charged hydrogen ion, or H plus for those in the know.
Mhm.
A Bronsted acid is the one tossing the proton, donating it to something else,
Okay.
and a Bronsted base. Well, they're the ones stuck catching it, or in technical terms, accepting the proton.
Sounds simple enough, but I'm guessing it gets a bit more complex than that.
You know me too well.
Uh-oh.
Let's bring back our friend hydrochloric acid, or HCl, the one making your stomach do backflips after that spicy burrito.
Always a crowd favorite.
It's a classic Bronsted acid.
Okay.
In your stomach, it's swimming around with a bunch of water molecules.
Right.
And water's a bit of a chameleon in the world of acids and bases.
A chameleon? Do tell.
It can act as either an acid or a base, depending on who it's hanging out with.
Okay.
In this case, with HCl being such an eager beaver to donate that proton, water steps up and acts as the base, accepting it.
So HCl throws the proton at water and water just goes with the flow.
Pretty much. And this is where it gets interesting.
Okay.
The HCl, after giving away its proton, becomes Cl.
Okay.
Now, Cl's feeling a bit proton deficient, so it could easily accept a proton back.
Right.
That makes it the conjugate base.
So like if the proton game continued, it'd be ready to catch the next one.
Exactly. Meanwhile, water, now sporting an extra proton, becomes H3O+.
Right.
It's become a conjugate acid because now it has a proton to potentially donate.
Okay.
Think of it like lending a friend $5.
Okay.
You're now in a proton-deficient state, like a conjugate base, while they're proton-rich, like the conjugate acid.
Okay, I'm with you so far. But how do we know how eager these acids and bases are to toss or catch these protons? Is there like a power ranking system?
You read my mind, and you're right. Not all acids and bases are created equal.
Right.
Some are like, get this proton away from me,
Yeah.
while others are a bit more hesitant to join the proton party.
Yeah.
That's where acidity constants and basicity constants, Kb, come in.
So it's like a measure of their enthusiasm for protons.
Exactly. A high K means a strong acid one that's practically jumping out of its skin to donate that proton.
Gotcha.
A high KK means we've got ourselves a strong base ready and waiting to snatch up any stray protons in the vicinity.
So the higher the number, the more reactive they are.
You got it. And this isn't just some abstract concept either.
Okay.
The strength of an acid or base determines how quickly and dramatically a reaction will occur.
Right.
Imagine a strong acid like, take this proton. No, seriously, it's yours. I don't want it.
Sounds kind of dramatic for a bunch of molecules, but I get the picture.
Right.
But what about those overachievers of the acid world? The ones that can donate multiple protons?
Yes.
This lecture mentions something called polyprotic acids.
The multitaskers of the acid world.
Okay.
A great example is hydrogen sulfide, or H2S, the culprit behind that lovely rotten egg smell.
Right.
It's diprotic, meaning it can donate 2 protons.
And each donation has its own acidity constant.
You bet. But here's the catch.
Okay.
Each donation gets progressively harder. Think of it like squeezing a water balloon.
Okay.
The first squeeze, easy peasy.
Right.
But with each subsequent squeeze, it gets tougher and tougher.
So the first chi is usually the highest, and then it gets lower with each proton donation.
Exactly. And to keep track of all this proton chaos, chemists use something called distribution diagrams.
Okay.
Don't let the name scare you.
Okay.
They're actually pretty helpful.
Okay. I'm intrigued.
Yeah?
Tell me more. What are distribution diagrams all about?
Imagine a graph, right?
Okay.
One axis is pH,
Right.
which basically tells you how acidic or basic something is.
Right.
The other axis represents the fraction of each species present.
So like a pie chart that changes depending on the pH.
Got it.
Yeah.
So for our friend H2S, the diagram would show us at a specific pH.
Okay.
If it's mostly hanging out as H2S, HS, or S2.
Right.
Because remember, it can donate 2 protons.
Right.
It can.
Okay. So it's
Yeah.
like a cheat sheet to see how our polyprotic acid is feeling at different pH levels.
Exactly.
So,
And this, my friend, is super important for understanding real-world systems.
okay.
Where the acidity is constantly changing.
Right.
Like in our blood or even a lake.
Okay. This is making me realize how much chemistry is going on behind the scenes of everyday life. But it brings up another question.
Yeah.
We've talked about strong and weak acids,
Right.
but what actually makes one acid stronger than another?
Hmm.
The lecture hinted that the periodic table might hold some clues.
It's like the periodic table is a giant cheat sheet for chemistry.
Right?
Remember those periodic trends you might have learned about in school?
Yeah.
Well, they're not just some abstract concept.
Okay.
They actually help explain how atoms and molecules behave,
Right.
including how badly they want to gain or lose a proton.
Okay.
You call this proton affinity.
So like some elements are just born proton grabbers.
Pretty much.
Okay.
Let's take hydrofluoric acid, or
Yeah.
HF,
Okay.
and water, H2O.
Mm-hmm.
Now, fluorine over there
Mhm.
on the periodic table is more electronegative than oxygen.
For those of us who need a little refresher, what does electronegative even mean? It sounds kind of intense.
Basically, it means fluorine is a bit of an electron hog.
Okay.
It pulls harder on shared electrons when it's in a bond.
Right.
So in HF, that fluorine is pulling those electrons so strongly
Okay.
that it weakens the bond between hydrogen and fluorine,
Okay.
making it easier for HF to donate that proton
Okay.
compared to water.
So it's like a tug-of-war for the proton, and fluorine has a stronger group than oxygen.
Exactly. And we see similar trends when we look at groups on the periodic table.
Okay.
Take the hydrogen halides, HF, HCl, HBr, HI.
Right.
As you go down that group, the atoms get bigger
Okay.
and their grip on those electrons gets weaker.
So iodine at the bottom is the weakest electron hog.
You got it. And that means HI is the strongest acid in that group
Okay.
because that hydrogen is basically hanging on for dear life.
Wow. The periodic table really is a secret decoder ring for chemistry.
Mhm.
But the lecture mentioned that it's not always this straightforward. Something about solvents shaking things up.
You're talking about solvation.
Yeah.
And you're right, it's not always as simple as looking at the periodic table.
Right.
We have to consider the environment these acids and bases are in.
Okay.
A solvent like water
Right.
can actually stabilize or destabilize an acid or base,
Okay.
making it seem stronger or weaker than it would be on its own.
So the solvent is like the hype man of chemistry, either egging the acid on or telling it to chill out.
I love the analogy.
Yeah.
It's all about how the molecules interact with each other.
This is making me see acids and bases in a whole new light. They're not just these things in beakers in a lab. They're dynamic forces being influenced by their environment.
Exactly. And understanding all of these factors,
Yeah.
proton affinity,
Mm-hmm.
electronegativity,
Right.
and solvation,
Okay.
helps us predict how acids and bases will behave in the real world.
Which is super important for all sorts of things, right? Like knowing how to prevent corrosion or maybe even designing new materials.
Exactly.
Yeah.
But we've only scratched the surface here.
Right.
Remember we talked about 2 main definitions of acids and bases,
Okay.
Bronsted and Lewis.
Right.
And things get even more interesting when we delve into the world of Lewis acidity.
Okay, I'm ready for it.
Yeah.
Hit me with the Lewis definition.
So think of Lewis acidity as Brunsted's cooler, older sibling.
Okay.
It's a bit more expansive, a bit less concerned with the rules.
Okay.
A Lewis acid isn't fixated on just protons.
Right.
It's all about accepting an electron pair
Okay.
and a Lewis base.
Yeah.
It's happy to donate an electron pair.
Okay, so it's not about protons anymore, it's about electrons. What's the point of having two different definitions?
It's all about having different tools for understanding the world.
Okay.
The Bronsted definition is great for a lot of reactions.
Right.
But the Lewis definition encompasses a much wider range of chemical shenanigans.
Okay.
It helps explain things that Bronsted just can't. For instance, metalcations. Those positively charged metal ions often act as Lewis acids.
Right.
And guess where this happens?
Let me guess everywhere.
You're getting warmer.
Okay.
I'll give you a hint.
Okay.
You're a walking, talking example of Lewis acid-base reactions.
Oh, really?
Think biological systems.
Wait, like inside our bodies?
Bingo.
What?
Let's say a metalcation like magnesium, Mg2+, is hanging out with an enzyme.
Okay.
Mg2+ is short a couple electrons, so it eyes up the enzyme's electrons.
Okay.
When that Mg2+ binds to the enzyme, it's accepting a pair of electrons in the enzyme.
Right.
That makes Mg2+ a Lewis acid,
Okay.
and the enzyme a Lewis base.
Whoa, I never thought about it like that, but it makes so much sense.
Right. Lewis acidity is happening all around us.
Wow.
And it's not always obvious.
Right.
Remember, it's not just about proton transfer anymore.
Right.
It's about electron pair shenanigans.
My mind is officially blown.
Right.
So we have Lewis acidity going on in our bodies. But are there other examples?
Oh, yeah, tons.
The lecture also mentioned something about carbon dioxide being a Lewis acid, and that seems wild.
It is wild.
Yeah.
But it all comes down to how CO2 reacts with water.
Okay.
When CO2 dissolves in water,
Right.
it can actually accept an electron pair from a water molecule.
Okay.
This little meet cute leads to the formation of carbonic acid,
Right.
which is a key player in ocean acidification.
Okay. That is way more than I ever thought I'd know about acids and bases.
Right.
And it's actually incredibly interesting. It's amazing how these seemingly simple concepts can have such huge implications for things like, well, the fate of our oceans.
Exactly. And the rabbit hole goes even deeper.
Oh, no.
This lecture also touched on how Lewis acidity plays out across the periodic table,
Okay.
just like we saw with Bronsted acidity.
Okay.
Certain trends can help us predict which elements are more likely to act as Lewis acids or bases.
Okay, spill the tea. What kind of periodic table trends are we talking about with Lewis acidity?
Well, for starters, that quirky little element, beryllium,
Right.
hanging out atop of group 2,
Okay.
tends to be a bit of a rebel.
A rebel.
Because of its small size and high charge density, it forms unusual bonds,
Okay.
making it a surprisingly strong Lewis acid.
So beryllium marches to the beat of its own drum,
It does.
even in the world of Lewis acidity.
Yep.
Got it. What else?
Then there's boron trifluoride, or BF3 as we like to call it, in the chemistry world.
BF3 sounds familiar.
Yeah.
Why do I know that?
It's a celebrity
Okay.
in the world of Lewis acids.
Okay.
BF3 is a crucial catalyst,
Okay.
meaning it helps speed up other chemical reactions
Right.
without getting used up itself.
Right.
We're talking everything from making plastics to developing life-saving medicines.
Okay. BF3 is officially a VIP in the world of chemistry,
Oh yeah, big time.
and its claim to fame is being a Lewis acid.
That's right. Its ability to accept electron pairs makes it a superstar in the world of chemical matchmaking.
I love it.
And then you have cases like tin chloride,
Okay.
which is like a chemical double agent.
Okay.
It can act as both a Lewis acid and a Lewis base,
What?
depending on who it's interacting with.
Wow.
Yeah.
Talk about playing both sides.
Right.
So basically, understanding these trends in Lewis acidity
Yeah.
across the periodic table
Right.
is like having a superpower.
It is.
We can predict how different elements will react
You can.
and even manipulate those reactions to create new materials or speed up existing processes.
Exactly.
That's amazing.
Yeah, it's really cool.
Okay.
So this lecture ended by talking about how simple acids can become these complex polymers.
Okay, yeah, that was another part that left my brain a little fried.
Yeah.
How do we go from tiny little acids to these big, complicated molecules?
Imagine you have a bunch of beads,
Yeah.
right? You can string those beads together to create a beautiful necklace.
Right.
Well, in the world of chemistry, we can do something similar with acids
Okay.
through a process called condensation reactions. Simple acids can link together like those beads on a string to form much larger structures called polyoxoanions.
So they're like chemical building blocks.
You got it.
Wow.
And just like you can build all sorts of amazing structures with Legos,
Right.
these polyoxoanions are the foundation for some incredibly important molecules.
Like what? Give me an example.
Take polyphosphates, for example.
Oh, okay.
They're crucial for storing and transferring energy in living things.
Right.
Remember ATP, the energy currency of cells we talked about earlier?
Yeah. So that energy drink I had this morning to get through this lecture is relying on polyoxoanions.
That's right.
That's kind of mind-blowing.
Yeah. That is why...
And it's not just energy drinks. These polyoxoanions are everywhere.
Okay.
Let's not forget silicates,
Right.
the most abundant minerals on Earth.
Okay.
They're what make up rock, sand,
Okay.
and even the screen on your phone.
Seriously, my phone screen is made of acid building blocks.
It is.
Okay, this is officially way cooler than I ever thought acids and bases could be.
Wow.
And just when you think it can't get any more fascinating,
Oh, no.
we have polyoxymetallites.
Polywashes?
Polyoxymetallites.
Okay.
Think of them like molecular skyscrapers.
Okay.
These intricate 3D frameworks made up of metal oxide units all linked together.
Okay, that sounds way too complex for me to even picture.
Yeah.
Like, what is that?
They're very cool
Okay.
and useful. Scientists are currently using them in cutting-edge fields like catalysis, speeding up reactions, and even analytical chemistry, figuring out what stuff is made of.
So we've gone from simple acids and bases to the building blocks of life and even the future of technology. This deep dive has been a wild ride.
It has.
My brain is like fried in the best way possible.
That's the thing about chemistry, isn't it? It's everywhere and in everything,
Right.
even if we don't always realize it.
Acids and bases, I had no idea.
Right.
This is amazing.
This is a good one.
Thank you so much for breaking all that down for me.
My pleasure.
And for everyone listening out there, go try some science at home. See you next time.